So this is there's three possibilities: forward bias, reverse bias. Okay,
Okay.
that's called biasing. For that to happen, obviously you have to apply appropriate voltage here and here. If you apply negative voltage here, they will be forward biased. Okay, so forward active means both emitter base forward bias, collective emitter base forward bias and the collective base reverse bias. This is a normal mode. It's called active mode. Access amplifier. Okay. Saturation means both should be on or both should be forward biased. Emitter base and collector base forward biased. The large current will flow. It's like a closed switch. Cutoff means both should be reverse biased.
Mm.
It's like an open switch. Okay, so there is slight difference between emitter and collector. It's not in the sense this thing reverse bias and this thing forward bias is not that useful. So there is slight difference between emitter and collector. So this is that. Okay. So one possibility is common base configuration. So this is a circuit diagram. Input is between emitter and base, and output is between collector and base. Base is common to both input and output circuit. Input circuit, we have this voltage source. Output is a voltage source. This is a biasing voltages because this condition has to be satisfied. This is a forward biased. This is a reverse biased. This one, they are represent this transistor bias symbol.
Mm.
So this is common emitter. This one, this one. So this is emitter. One other one is collector. So in this, I think it's clear because arrow mark is always put in the emitter, and this is P. Arrow is from P to N. This is P.
Okay.
This is N. Obviously, this should be N. So this is NPN transistor. Okay. So this is forward biased. And this is emitter. Ask them to go on far away and talk. So yeah, so this thing is reverse biased because positive terminal is connected to N. You attract the electrons, so depletion region will be larger here. Here will be narrow. This junction. And the third possibility is common collector. So this is C between input and output. They are all taking NPN. Okay. So they have taken common base configuration to study in detail. Okay. So here, base is common. This is emitter on the input side. So electrons flowing in this direction because you get repelled. But the current will be opposite to the direction of the negative charges. Holes will flow in this direction, but here hole is minority carrier because hole is only majority carrier here. Here and here it's minority carrier. So most current will come from majority carrier. So electrons will give the maximum current here. So large number of electrons will flow here. Few electrons will flow in this direction because of the geometry. And this, you know Kirchhoff's current law, right?
Yes.
In a junction. I have a junction like this. So this current, say this is going out, this is going out. Let me call it 1, 2, 3. So I1 entering equal to leaving I2 plus I3, right? Similarly, have more thing like this. Suppose I have a fourth one here and fifth one here. So 4, 5. So we apply this rule in this node. It will be just disappear. Oh God. Hey, someone is making disturbance in the background.
Okay.
Okay. This is 1, 2, 3, 4, 5. So in this node, 1, 2, 3, 4, 5. I1 equal to I2 plus I3. So in this node here, this one, entering is I3 plus I4 equal to I5. Okay. Suppose if I add these two, I'll get I3 will cancel on both sides. It will become I1 plus I4 equal to I2 plus I5. Is that clear? Add the first two. Okay. So that I can understand as writing KCL in this. Consider this is a super node. Okay. So whatever current is entering the surface, which is I1 and I4, and the currents that are leaving are I2 and I5. I3 is inside. It's not entering or leaving. Okay. So KCL is not only applicable to a node, it also applicable over a surface. You can take its surface or a curve, or a closed curve. Whatever current is entering should match the leaving ones. So if I take this circle, the current entering is 1 and 4, leaving is 2 and 5. Okay. So for this transistor, this one, IE could I be precisely right? I can take a surface like this. Okay. Current leaving the surface is IE. Current entering is IB and IC. So IE should match IB and IC. That's what this equation is. Okay. So they put Kirchhoff's law, which is applicable for a node, but here it is like a super node or a surface. Okay. Obvious, right? Common sense. Whatever is entering should leave, others will be accumulation, which is not allowed because it's steady state. Okay. So, and I have to choose the direction properly. I have to mark IE like this and IB in opposite. If I put IE like this, that's not correct.
Okay.
IE is emitter of charge carriers. So if you put the other one, IC is a collector, so it will be opposite. It will be inverse. B is also inverse because emitter is the dominating one.
Okay.
Okay. Even for PN transistor, the thing will be reversed. IE will enter, IB and IC will leave. So this thing is valid if you choose the directions properly. IE is entering or leaving, and IB and IC are the opposite. Here, NPN transistor I is leaving, and these two are entering.
Okay.
Okay. Another thing is, by design is, this usually this current will be small. Base current will be small. That's why they shown figuratively here by a small arrow. If you this is a thick arrow, it's a little bit less. So if this is 1 means it will be 0.9 amps, this will be 0.1 amp. Okay. So that's why they have said it's approximately IE and IC are same. Just a minute.
Okay.
So that means IB is approximately 0.
Hmm.
Okay. And forward current gain. So it's output by input. So in this common base configuration, output is collector, input is emitter. So output, you can consider as output current IC by IE. That is one parameter, alpha, IC by IE, this you have to remember. P impedance is similar to NPN, except that emitter current is due to holes. PNP means maximum P region, right? So current carriers will be holes. In NPN, maximum region is N, where free electrons are available. So the maximum current is due to the electrons. So it's just a simple thing. Transistor containing common base configuration, alpha is 0.95. Alpha will be close to 1 because it's output by input, which is IC by IE, and IC is approximately IE because IB is very, very small. Okay, so it will be close to 1. And IE is 1 milliampere, calculate IC and IB. So when alpha is known, this ratio, IE is given, so IC is known. So IC is 0.95. For input emitter current being 1, 0.95 is emitter current. So obviously the base will be the remaining 0.05. Is that clear?
Oh, yes.
Like resistor, the thing that will specify that resistor properties of ohms, 5 ohms. Similarly for transistor, there are properties like alpha, which is the ratio of IC and IE. So for a given transistor, alpha is fixed. Like for a given resistance value is fixed, right? So similarly for a given transistor, alpha value is fixed. So common emitter mode. So this is the common emitter configuration. This is a transistor. So arrow mark is from P to N. So this one is P. This one is N. So this one is N. So this is NPN transistor. And emitter is common. So emitter is in the middle. So input is base. Collector is referred to the output side, base on the input side. So here you have to apply a voltage here. So you have to apply such that this should be forward biased in the active region. This should be reverse biased. So this forward bias means this is P. So if we apply a positive here, it will repel the holes towards the junction. So junction will become narrow. And this junction will become wider because this positive will attract the holes here, will become the okay. So there is a so IB current is this measured by this meter ammeter, and this VB is measured by this voltmeter. There is a voltmeter here. There is a ammeter here. So IB is in micro. Collector current is milliamps. So this also in milliamps, but once I know these two, I can, this plus this will be this one, IB. IB and IC are entering, IE is leaving, so IE equal to IB plus IC. So if I know these two, I'll know this one. I just add them. So for a resistor, the two parameters are voltage and current, and the ratio of that is the resistance value. But in the case of transistor, there are three currents, IB, IE, and IC, and there are two voltages. One is the input voltage, BE, and another is the output voltage, VC. So one thing we can define is input characteristics, that is VI relation from the input terminals. So V on the input terminal is this common emitter, right? So BE, and the input current is base current. So IBE versus IB is the input characteristics, or IB should be the y-axis, and then voltage is the input voltage VB.
Uh,
Okay, input side is BE, current is IB.
okay.
So this is the input characteristics. So this will be like a forward bias diode. On output characteristics on the output side, the current is
No.
IC and the voltage is between C and E. So IC versus VC, because common emitter configuration, emitter is common, collectors on the output side. So because IC versus VC. Okay, and this thing is reverse biased. It's reverse biased, no? Current is less. Yeah, so it is that part of the very first VI, this one, it is this part,
Mm.
reverse bias. This one. So current will increase, and so that there it is shown in the third quadrant. Here will come in the first quadrant because this thing has been chosen that way. Okay, so this is the saturation current in the reverse direction. So it's in the microamps. This will
Okay.
be amps. So this base current will be small. Here it is. Okay, base current is fine. So this is output characteristics, IC versus VCE, and
Mm.
one more is transfer characteristics, which is output and input, or output is the output terminal, which is the collector, IC. It's common base configuration, common emitter configuration. So the input current is IB. So how are IC and IB related?
Mm.
IC versus IB. Okay, IC will be milliamps, even IE will be in milliamps, but base current will be small, will be in microamps. So input impedance is on the input side. You have to find impedance is same as resistance that you have studied, no, in AC chapter. It's
Yes.
R plus X square of R square plus X square, right? So here they have said impedance in general, but it's actually resistance. So on the input side, the voltage is VCE and the current is IB. So input impedance is VCE by IB.
Okay.
Hold on. Input voltage between base and emitter, right? Input is base, common thing is emitter. So input voltage is between base and emitter, and the current is base current. Okay. So for a resistance, uh, VI will pass through the origin because when voltage is zero, current is zero.
Mm.
This is I, this is V. So resistance is slope of this line. This I can define as delta I by delta V. Actually, the slope here is 1 by R because current is on the y-axis. But this same slope I can get between these 2 points from the origin and any other point. So this will be I, this is V. So slope again 1 by R is I by V. So what I want to say is resistance is not only just V by I, it's also delta V by delta I. This is
Okay.
more appropriate because if it's not a straight line, delta V by delta I will be different from different points. So this is a curve like this.
Mm.
Here delta V by delta is different from here. For a straight line, it is same. Whether delta V by delta I or V by I, it is always same. That's the property of a straight line. But since
Mm.
this for a transistor, it's not straight line. So resistance is more appropriately defined as delta V by delta I. Okay, because if I do this delta VB, what is the input? Now this will be, so here, if we take these 2 points
Mm.
and do this delta VB by delta I, and if we take these 2 points, it will be different because it's not a straight line. Here the slope is maximum. Okay, so slope is 1 by R, is more here. Here 1 by R is less. So here resistance is more here. Here resistance is
Okay.
less, small r. Here capital R. Okay. So in general, for a thing which is not a straight line, which is curve in general, more appropriate to define resistance is delta V by delta
Okay.
I. Okay. And for a given VC, because you get different comes for different VC.
Mm.
If you have two variables, I can plot one of them here and second one here, and I'll get one curve and see for some parameter value P1. For the second parameter, I'll get a different curve P2. Because in 2D, this thing I can have only two variables. The third variable will be parameter of the curve. So here,
Mm.
the two variables are just base current and this VB, which is the input side, and there is one more voltage VCE, which is on the output side. So depending on that value, the curve will be different. So that is put as a parameter. So this is given for a given VC, that means you have to choose one particular curve, and then we have to find R at different points. Okay. So this means for a given VC. So for 2 volts means you have to choose this curve. For 1 volt, I have to choose this curve. Similar output
Okay.
characteristics. Uh, Output impedance. So output voltage is VCE and the output current is IC. Emitter is common. So for this is for a given other parameter of this thing is IB.
Mm.
So this thing they are drawn for different IBs, right? So I have to choose one particular IB, that is choosing one particular curve, and then do this delta V by delta I to get the resistance. So that's a measure of resistance, delta V by delta I. So that's called output impedance because it's during the output terminals.
Okay.
So this curve you have to remember. This is the third quadrant of the first VA crossover diagram. This is the first quadrant of that plot, the input impedance. Okay. And this is the new one. Just studying in this for transistor, not for diode. Output current by input current will be a straight line.
Mm.
So, so this one, like three modes I have said, right? Both normal mode, which is the emitter junction is forward biased, and the collector junction is reverse biased. That is the active region. Emitter junction is forward biased, and the collector mutual junction is reverse biased. Not
Mm.
collector divergence, collector base. Collector base. Junction is
Okay.
always between base and emitter and base and collector. Okay, I mentioned it wrongly here. Okay, so break this active region. Cutoff means both should be reverse biased. Okay,
Okay.
so and breakdown will happen if the voltage is high. Avalanche
Mm.
breakdown, and one junction should be reverse biased. Okay, there are two
Mm.
junctions in active region. One of them is reverse biased, so that reverse biased junction, if that voltage is high, there will be breakdown.
Mm.
This saturation region, again, this thing is reverse biased. So this part, output characteristics, this part is called the saturation region. So that corresponds to the third quadrant of the first plot. Basically, the diode, the first PN junction diode, this is how it looks like. This is the breakdown. So this is the knee voltage. Okay,
Mm.
so this is the saturation current. So saturation region is this one, this region.
Mm. Okay.
Spin. This region is saturation region where the current is almost constant. Here the current is increasing, here the current is increasing. So reverse bias, this region is called saturation region.
Okay.
So there is one more, like alpha I defined as output by input in the common base configuration, which is IC by IE. So similarly, there is
Mm.
one more parameter beta, which is forward current gain in the common emitter configuration. So common emitter, the output is uh, collector current, input is base current. So this is defined as IC by IB, but more appropriately it's as delta IB by delta IC by delta IB. Okay, so
Ah.
using that, I can get this relation.
Mm.
Like KCL, I have IB equal to IB plus IC. I've chosen the direction of emitters entering and these two as leaving. And alpha is defined as output by input in the common base mode. And beta is again output by input in the common emitter mode. Output is the collector current. Hold on. Beta is in the common emitter mode. Output is no, this one is mistake. This is emitter. Input is emitter in the common base configuration.
Ah.
In the common emitter configuration, input is base current IB. And so here, output by input. uh, So divide by IC throughout. So if I divide by IC this one, I'll get IE by IC. IE by IC is 1 by alpha. Okay. IB by IC is 1 by beta plus 1. So this is the relation between alpha and beta. 1 by alpha is 1 by beta plus 1. And remember, 1 by alpha is more compared to 1 by beta by a number 1.
Okay.
This relation, if you simplify, you'll get this one. This is same as this one. And the proof of this one is definition of alpha and beta and the KCL. IE equal to IB plus IC. If you use these three, you'll get this relation. And one more thing you should remember is alpha is close to 1, for example, 0.99, and beta is high. It's around 100. So if you put 0.99 here, beta is 100.
Okay.
For example, in this one, alpha is, we are not given. Beta is 125, so alpha will be correspondingly different. But one thing is always true, alpha is close to 1 and beta is large, because beta is IC by IB. IB is small current, IC is big current, even IE is big current, but IE is more than IC. So this way, this is, and IC and IE are close. So alpha is close to 1, but less than 1. Beta is large. So you can solve some simple circuits. For example, in the circuit shown below, voltages are given. You have to find IB, IC, and beta. So this is 0, VBE. Okay. VB is given. VB is 0 volts. So that means this is forward bias from here to here. It's 0 volts. So it's forward bias. So this is 0. This is VI. VI value is also given. VI is 20. So this is 20 volts. So this current will be 20 by 500. 20 by 500. That is 2 by 50. It's 1 by 25 micro, because this is king. That's actually milli. And one more, this thing will give me micro. Okay. This you can do the calculation, right? 1 by k will give me milli. But since this number is large, that will make it micro. Similarly, IC is, how to know this voltage? So VC should be given. VC is also given. 0 volts. So from here to here also 0 volts. That's possible because one thing is forward biased, other one is reverse biased. So even when the diode is forward biased, there will be a drop of 0.7 volts corresponding to the knee voltage. So suppose this is positive, and then so the drop from here will be this 7 volts corresponding to this one. Suppose you have another diode like this, and this is plus, so this is reverse biased. Sorry, this is more negative compared to this one. So this is reverse biased. So here the drop will be from again here to here, but it's slightly more than 0.7 volts. So again the drop from here to here is approximately 0. It's like having two cells, one like this, another like this. So this is 3 volts, this is 2.9 volts. The drop from here is 0.1, which is approximately 0.
Okay.
So same thing for a transistor. Across CT is also the voltage is close to 0. This is close to 0 because of the forward bias. This is close to 0 because the two voltages will opposite each other. So that's why VC is 0. So this is 0 volts, this is 20 volts. So 20 by 4K is the current in this one. So 1K will give me milli, and this is a big number, so it's milli. And beta is the output by input in the common emitter mode, which is the output current by the input current, 125. So these are simple problems you will ask. So these things you should see, otherwise you will not able to solve the question.
Um,
So this one, common emitter. Emitter is common. So this is the input side, this is the output side. Okay, another simple thing I want to explain. See, for a resistance, this is I, this is V. So if I apply this voltage, this value of voltage, I'll get the corresponding current. If I apply voltage of this value, I'll get the corresponding current. Okay, but suppose I apply a time varying voltage where the voltage varies from here to here like this,
mm,
then the corresponding current will also vary like this.
mm,
Like for a resistance, if I apply AC voltage, the current will also be AC. Okay, so in general, you can understand like this. I'll whatever waveform I apply the input, the corresponding waveform output I can get. So here, so if you apply sine and the curve is a straight line, then the corresponding output will also be a sine. But suppose it's not a straight line, but it's distorted like a curve. Okay, then this output sine will also be distorted. Okay, only straight line has this property. If the input is sine, output will be sine. So that's why you have to operate this transistor. I can change the VCE from in this region about this point Q. If I change, I'll get a corresponding sign variation in this output also. So that's why you have to
mm,
choose this. This Q is called operating point. See, for a resistance, say I'm changing the voltage from peak to peak with some at this particular value. Okay, I can also make this variation at this point and get the corresponding output here. For a resistance, it does not matter because wherever I put, I get a decent curve. But if the thing is not a straight line, it's a curve, I have to choose a proper region where it's approximately straight line. Only like the nice output. So that's important to choose a appropriate point for this one. So this choosing point, it's called biasing.
oh,
Um, so you can apply AC voltage like this. This is zero, this voltage. I can apply AC voltage. I can also apply AC voltage like this, which there is variation is there with this bias. Okay, suppose this is 5 sine omega t. This is whatever this voltage is 6 volts plus 5 sine omega t. This is just 5 sine omega t. This is without the bias, this is with the bias. So this bias makes me to choose this point properly, about which I can give the variation. That's
mm,
operating point. So here the bias point is Q for the operating point, Q point, middle of the DC load line to
mm,
work effectively as amplifier. So that the variation is within the straight line part.
okay.
Beta is, yes,